studied about the center of gravity. So let me recapitulate it what we have studied until now. So we have studied that what is the center of gravity first of all. Center of gravity, that is a fixed point in the body through which the weight of the body passes. So that is the point. Suppose you have this body and there would be some point inside this body such that whole of the mass of the body is concentrated at this particular point. So that is its definition. Next is for a system of particles. Suppose now instead of body or some mass or some matter, you now have certain particles. So now these particles would also exhibit the same property. So that means we are saying the mass of whole of these particles that would be situated at some single particle over here or some single position over here. So if I denote the position of this particle say by x1, y1 and its mass by m1, second particle would be x2, y2, this is the position vector and its mass is m2, and then the third particle would be x3, y3 and its mass would be m3 and so on. Suppose we have n particles, suppose this is the nth particle, so we have the position as xn, yn and its mass would be mn. Then all of these points, they would have certain coordinate here as the center of mass, center of gravity, and we call the coordinates for this as x bar and y bar. So that is the notation. So this is the discrete nature of particles. That means we have n particles which are present at different locations in space. So that is what we have studied, that this x1, y1, x2, y2, xn, yn, these represent the positions of these n particles, and m1, m2 up to mn, that represents the masses for these n particles. Now the center of gravity for that particular system, that would be the x coordinate that is given by this expression. So that means what we are saying the mass corresponding to the sum of masses corresponding to the x coordinates divided by this total mass, and the sum of mass corresponding to this y coordinate divided by this total mass. So this is the corresponding y coordinate and this is the x coordinate. So this is the simple definition when we have a number of particles, say n number of particles. Now suppose you have this curve. So now this curve is made up of a number of points, and the number of such points, they are infinite. So can we relate this curve to a system of particles? Yes, because every curve has an infinite number of points, infinite number of particles embedded into it. So this is a more general case of the previous one where we have studied about only the n particles. So now in curve we have continuous nature of particles, so one particle cannot be distinguished from other. So these are very minute and tiny particles which are present on this curve. So let me call certain portion of this curve, this one, as say delta s, the small arc length. Then I say the position of this particular point would be x, y, and the position of this particular point would be some increment in the previous position x, representing by this delta x, and some increment here in the position of y, representing by delta y. So this is the 2 point, and this delta s is the small arc length. So now next, to calculate the center of gravity for a plane curve, what we need here, because the curve that would have different nature at different coordinates, so its mass would also be different at different points. So we say this curve would have the mass as defined like this. Rho is the mass per unit length. Mass per unit length. So if you wanted to calculate the mass here in this particular region of this curve, so it would be nothing but rho multiplied by whatever length it would have. So say dx. So that is the mass associated with this particular portion of the curve. So we say if rho represents the mass per unit length of the curve y is equal to f of x, then this small portion would be mass of the small portion. It is represented by delta m. This is the notation, and this mass would be equivalent to whatever distance of this portion is there, that means delta f, and that is multiplied by this per unit length mass. So total mass would be the integration of this small mass. So total mass of this curve would be integration of rho delta s. So we have this total mass. Now what would be the center of gravity for this particular curve? So it is again represented by this coordinate x bar and the coordinate y bar and their coordinates, and it is calculated now using this expression x multiplied by the given mass. This is the small portion of mass that we have, because initially earlier we have this formula summation xi divided by summation mi. Now because we have infinite number of points here, the summation is converted to integration, and moreover this mi is now the small piece of mass, that is rho ds. So this is rho ds. So we have integration x rho ds divided by this total mass, integration rho ds, and y is again integration. For y we had this formula summation yi mi divided by summation mi. So summation is replaced by integration, and this mi is represented by del rho del s, right? So it is the sum of masses in x coordinates or y coordinates divided by the total mass. So now what is this ds here? Or if we have our curve defined in this Cartesian equations, so what is this coordinate? So for this Cartesian coordinate, suppose this is your curve. So what we can do, we can draw a perpendicular here in the vertical direction, and we can draw a perpendicular here in the horizontal direction. So now they would be perpendicular to each other. This distance would be dx and this small distance would be dy. So what would be this ds whenever this length is small? We can ignore this curve for the small length. So it would be ds whole square, that is equal to dx whole square plus dy whole square, because of Pythagoras theorem. So hypotenuse square is equal to base square plus perpendicular square. So it is like this. So here this is base and this is perpendicular and this is hypotenuse. So accordingly we have ds is equal to square root of dx square plus dy square, and then we can take this dx square common, so we will have this quantity. So the value of ds is this one whenever our curve is Cartesian in nature. Now if your curve is parametric in nature, so that means you would have x is equal to some function f of t and y is equal to some function g of t. So in that case this quantity ds square, that is nothing but square root of x square plus y square. But now the derivative has to be performed with respect to t, because x is a function of t, y is also a function of t. Therefore we can perform this derivative with respect to t. So it would be, if I am writing square, I should not write square root on the right hand side. So here I am removing this square term. Okay. So we have ds upon dt. This would be equal to dx divided by dt whole square plus dy by dt whole square root. So now this quantity is equivalent to this quantity. So therefore this is the expression that we use for the parametric case. And for the polar case, for the polar curves, what do we have? We have x is equal to r cos theta and y is equal to r sin theta. So here what is this derivative? Dx, it would be the derivative of this quantity. So here we have two terms, so we will differentiate it using the product rule. So first function as such, the derivative of second, it would be minus sin theta d theta, and then plus the derivative of first, that is dr, and the second term as such. So this is the differentiation of this curve x here. And when you differentiate this y here, you would have dy, that is equal to first function as such, then the derivative of second would be cos theta d theta, and then first function's derivative and sin theta as such. So say this is our equation number 1, this is our equation number 2. So from here what do we require? We require ds square, that is equal to dx square plus dy square. So what does it become? It becomes the square of this quantity. So it would be r square sine square theta d theta square plus, and then it would be dr square cos square theta, and then it would be minus 2 times r sine theta cos theta dr and d theta. So this is the square of this dx term, and then we can square this dy term as well. So it would be the square of first term, that would be r square cos square theta d theta square. Then the square of second term would be dr square sine square theta, and then the 2 plus 2 times first term into second term. So 2 times r cos theta sine theta dr d theta. So this is the quantity that we obtain. Now from here you see this term 2r sine theta cos theta dr d theta is equivalent to this term 2r cos theta sine theta dr d theta. However, they have opposite signs. So this whole term cancels with this whole term, and here in this term and in this term we have r square d theta square common. So we would write this to be sine square theta plus cos square theta, and here we have dr square common. So we can write this to be dr square sine square theta plus cos square theta. So now because sine square theta and cos square theta, they are equivalent to 1, so we are only left with this quantity. So our ds square becomes this thing. So can we write this to be ds upon d theta square? Yes. What would be this? This would be r square plus dr upon d theta square. Or in other words, for polar cars, your ds upon d theta, this becomes square root of r square plus dr upon d theta whole square. So this is the quantity that we got here. For polar cars, we got this quantity. ds is nothing but the square root of r square plus dr upon d theta whole square d theta.